have here a polynomial and I want to find its complex zeros. First I'm going to do Descartes' rule of signs. So I have a positive, a minus, a positive, and a minus. That's 1, 2, 3 variations in sign. So for the positive zeros there can either be 3 or 1. And for the negative zeros there are 0 of them. So that's convenient. So we don't have to test any negative numbers. So next let's find the possible values for the zeros. We do that with the P over Q test, which is the coefficient of the constant and the coefficient of the leading term, the factors of the constant, which is minus 17, plus and minus 1, plus and minus 17. And the factors of the leading coefficient are plus and minus 1. So the possible zeros are plus and minus 1 and plus and minus 17. So let's start factoring. Let's start with synthetic division. We'll do 1. We only have 1 and 17 as possible zeros. And we can have 3 or 1 positive zeros. And it's most likely going to be 1. The only way it can be 3 is if there's a multiplicity of one of these factors. So let's look at our equation to set up our synthetic division. We have 1, minus 9, positive 25, and minus 17. Let's carry out the synthetic division. We bring down the 1. 1 times 1 is 1. Minus 8. Minus 8 times 1 is minus 8. This is going to give us positive 17. Positive 17 times 1 is positive 17, and we get 0. So 1 is a 0. So we factor out a1, x minus 1, and we're left with x squared minus 8x plus 17. And this is in quadratic form. Oops. There we go. This is in quadratic form, so we don't really need to go around testing random numbers now. We can either look at this and figure it out by eye. So we need two numbers that multiply to be 17 and add to be 8, and I can't think of any. So what I'm going to do is just use the quadratic formula, which is x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a, not including the x. So now I'm going to fill in this formula. X is equal to negative b, which is minus 8, plus or minus the square root of b squared, which is minus 8, squared minus 4ac. A is, I forgot to put the 4 in there. 4, a is 1, c is 17. And this is all being divided by 2a, and a is 1. So if we simplify this, this is going to give us minus minus 8, which is positive 8, plus or minus the square root. 8 squared is 64. 4 times 1 times 17, 4 times 10 is 40, 4 times 8 is 28, so this will be 68. This is all being divided by 2. This is going to bring us 8 plus or minus the square root of negative 4 over 2. And now that we know that we can include complex numbers due to the fundamental theorem of algebra, we can solve this equation. We can say that this is equal to 8 plus or minus 2i over 2, which is 4 plus or minus 2i. So we have both answers. So our other two zeros are 4 plus 2i and 4 minus 2i. So let's write out all of our zeros. Now our zeros were 1, 4 plus 2i, and 4 minus 2i. Or if we want to write this out as a series of linear factors, we can write it out as x minus 1 times x minus 4 minus 2i times x minus 4 plus 2i. That's a little bit scrunched. Or we can write it out like that. Either way is fine. I have a couple more problems, and each one of them has a different element to it. So let us try. And these ones are going to be a little bit longer. These are going to be x to the 5th powers. So f of x is equal to x to the 5th minus 11 x to the 4th plus 19 x to the 3rd minus 17x squared plus 17x minus 6. And I want to find all of the zeros for this polynomial. Again, it's always best to start with Descartes' rule of signs. Plus, minus, plus, minus, plus, minus. So we have 1, 2, 3, 4, 5 variations in sign. So for our positive zeros, we're going to have 5 or 3 or 1. And again, we're going to have no negative zeros. So now let's do the P over Q test for this. So P over Q, coefficient of the constant, and the coefficient of the leading term. So the constant term here is 6. So we're going to have plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. And here the coefficient of the leading term is not 1. So we're going to have plus and minus 1 and plus and minus 2. And I need to give all of the possibilities of these combinations. So let's do 1 first. So our possible zeros are going to be plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. And now for 2, we have plus and minus 1/2. 2 over 2 is still 1, we already have that, so we can ignore that one. 3 over 2, so plus and minus 3 over 2. And then 6 divided by 2 is 3, and we already have that one, so we can ignore that. So here are our possible zeros. And the good thing about this problem is that there are no negative zeros, so we don't have to test the minuses at all, because there are none. So at least we don't have to do that. But let's start testing these zeros then. Let's start with, we might as well just start at the beginning and then go out. So I have 1. And let me see what the coefficients are. We have 2, minus 11, 19, minus 17, positive 17, and minus 6. Bring down the 2, this is 2, minus 9, minus 9, positive 10, positive 10, minus 7, minus, oops. Minus 7, 10, 10, and we get 4. So this is not a factor. 1 is not a factor. Let's try 2 next. We have the same coefficients. So we have 2, this will be 4, this will give us minus 7. Minus 7 times 2 is minus 14, this will give us 5, which will give us 10. Minus 7, minus 14, which will give us 3. And then this will be 6, and then we'll get 0. So 2 is a factor. So what we've just done, I always like writing these out in linear factor form, just so everyone can understand what has just happened. So we've just factored out an x minus 2 because we know that 2 is a 0 and therefore a factor, so x minus 2 is a factor of the original equation, and what we're left is this. Now, there are some. Now, the reason I pulled up this problem is because there are some shortcuts. Here, we have a lot of zeros. And when you have a problem with a lot of zeros, if we divide something out, what I can do is I can take a new pool of numbers from here. Because factoring this is the same. It would be just like this equation is the same as this equation, except it's being multiplied by this. This equation is the same as the original equation, except it is being multiplied by an x minus 2. So if we're presented with this equation, pretend that this x minus 2 was not here, we could factor it out the same as if it was a brand new equation. So if I wanted to, I see that these numbers are smaller. I see I have a 3 for the constant and a 2. So what I can do, if I feel like it, and I do feel like it because I'll be able to eliminate some answers, I can take a new pool of numbers, a new p over q, for this. I can say, well, the constant is plus and minus 1 and plus and minus 3. And for the coefficient of the leading term, it's plus and minus 1 and plus and minus 2. So my possibilities are plus and minus 1, plus and minus 3, and then plus and minus 1/2, and plus and minus 3 over 2. But we already tested 1 and that wasn't it. So for this polynomial, the possible zeros are plus and minus 3, plus and minus 1/2, and plus and minus 3 over 2. And what I can do is eliminate 6. I was only able to eliminate 1. But in other questions or in other problems, you may eliminate quite a few more. So I thought I would just take the time out to show that this is a possibility. And it probably is not really suggested in your books. But this is one of those things that if you do a lot of problems, you'll figure out that, yes, you can do this, and theoretically it should be just the same. And I just wanted to confirm that in case anyone was thinking that yes, you can do the P over Q test again once you've already factored something out. And yes, in some cases it will eliminate a lot. In this case, it would have only eliminated 6. We would have done 6 and found out that it was not a factor. But anyways, let's continue with our new set of numbers. So we found out that 2 was 1. So now we're left with a 3 plus and minus 1/2, but we know that there are no minuses because of Descartes' rule of sign. So we have to test 3, 1/2, and 3 over 2. So let's test 3. So we have 2, minus 7, 5, minus 7, and 3. Now 2, 3 times 2 is 6. This is minus 1. Minus 1. 3 times minus 1 is minus 3. This gives us positive 2, which gives us positive 6, which gives us minus 1, and this gives us minus 3. And 3 is also a 0. So 3 is a 0. So now what we have left is we've factored out that 2. Now we factored out a 3. Now we're left with x cubed minus 1, minus x squared. You can put a 1 in front of it if you want. Plus 2x minus 1. So now we've done 3. Now we're left with 1/2 and 3 over 2. And I can see here that 1/2 will work. So I'm just going to test that one first. So 1/2, 2 minus 1, 2 minus 1. So this is an easy one to see that 1/2 will work. So bring down the 2, times by 1/2, that's 1. This adds to 0, and then the same thing over again. We add a 0, we get 2, times it by 1/2, we get a 1, and then we get a 0. So 1/2 is also a factor. So now what we've got is x minus 2, x minus 3, x minus 1/2. And what we're left with is x squared plus 2, or 2x squared plus 2. And here we can see that this is going to be a quadratic with an imaginary number, because we can't put in any x and give us a 0, because we're having a squared, and any negative number is going to be squared, and then we're going to add a positive. But this is an easy one. We don't have to use quadratic formula. We can just say 2x squared plus 2 is equal to 0. We divide both sides by 2. We can do that first. So we divide both sides by 2. We get x squared plus 1 is equal to 0. I subtract this 1 over to the other side. X squared is equal to negative 1. And I take the square root. So this x is equal to plus or minus the square root of minus 1. And as we know, the square root of minus 1 is equal to I. So we say that x is equal to plus and minus I. So our zeros are 1/2, 2, 3, I, and minus I. So I should probably do that in a different color. There we go. Or if we want to write them out as a product of linear equations, we can write this out as x minus 1/2, x minus 2, x minus 3, x plus I, x minus I. However you wish to give your answer. And if we were to multiply all these out, we would get back our original equation. And I have one more that is a little bit tricky. It has a few tricks in there. I like tricks. Well, not really, but you just gotta throw them in there sometimes. So this one I have is f of x is equal to x to the 5th minus 2x to the 4th minus x cubed plus 8x squared minus 10x plus 4. First off, I'm going to do Descartes' rule of signs. I see I have a positive, a minus, a minus, a positive, a minus, and a positive. So for the positive zeros, let's see, we have 1 changes sign, 2 change, 3 changes, 4 changes. So we're going to have, for positives, we're going to have 4 or 2 or 0. And that means for the negative zeros, we're going to have just 1. So now let's find the possibilities for our zeros. So we have p over q, when in this case is going to be, the coefficient is plus and minus 1, plus and minus 2, and plus and minus 4. And for the leading coefficient, it's just plus and minus 1. So that means our zeros can be plus and minus 1, plus and minus 2, and plus and minus 4. And we said there are 4, 2, or 0 positive zeros. Here there are only 3. So the only way it can be 4 is if there is a multiplicity. That means if 1 is repeated, or 2 is repeated, or 4 is repeated. So it probably won't be 4, but it could be, you never know. And for negative zeros, there is only one of them. So let's find that one first, just to get it out of the way. So we have 1, 2, and 4. We'll try minus 1 first. We have 1, minus 2, minus 1, 8, minus 10, and 4. One minus 1 minus 3, 3, 2, minus 2, 6, minus 6, minus 16, positive 16. This gives us 20, so this is not a factor. Let's move on to minus 2. Same equation. One minus 2, minus 2, minus 4. This is going to give us positive 8. Minus 1, this is going to give us 7. Minus 2, minus 14. Minus 14, that's going to give us minus 6. Minus 6 times 2, well, that's going to give us positive 12, which will give us 2. Minus 2 times that, that's minus 4, and this is a 0. So minus 2 is a 0. So let's factor this out. So we've got x plus 2. And then we have x to the 4th minus 4x cubed plus 7x squared minus 7x plus 2. And you don't have to do this whole writing things out every time. I'm just doing this to make it clear on what is happening in case people are having trouble of what it is they're doing. People might be going through these steps and then just not understanding what it is they're actually doing. So this is why I'm writing this out unnecessarily every time. So we've done that. And let me check and see what zeros we have. Oh, we have plus and minus 1, 2, and 4. So here, if we want again, this is strictly optional. If you're not comfortable doing it, then we can just continue using this pool of numbers. But what I like to do is, if I can, eliminate any numbers, any unnecessary work I have to do. Is every time I'm doing synthetic division, I'm potentially going to make a mistake. And I don't like making mistakes. So what I do is I check my pool of numbers and I make a new pool of numbers from this new polynomial. So the p over q of this. So here's our coefficient is plus and minus 1 and plus and minus 2. And here we still have 1. Plus and minus 1 and plus and minus 2. Or no, not plus and minus 2, just plus and minus 1. So this means our potential zeros are plus and minus 1 and plus and minus 2. That's it. So by doing the p over q again for this new polynomial, because again, this polynomial is the same as our original equation, just times x minus 2. So I can redo everything. I could do the rule of signs again if I felt like it, but it's pointless. But this p over q test is something that is useful to do over again if you have a lot of numbers that you have to test. So I can eliminate 4. I know that that's not going to be 1. And we found our negative 0. So there are either going to be 4, 2, or 0 positive zeros. And it's unlikely it's going to be 4 unless these are repeated. But anyways, let's just continue now that we have p over q again. So let's test for the positives. All we have to do now is just test for positive 1 and positive 2 since we already have the negatives. So let's test for positive 1. 1 plus So we have 1, minus 4, 7, minus 6, and 2. 1 times 1 is 1, minus 3. 1 times minus 3 is minus 3. This gives us positive 4. 1 times 4 is 4, which gives us minus 2. 1 times minus 2 is minus 2, and this gives us 0. So 1 is also a 0. So now we have what was my other? Oh yeah, minus 2. Forgot there for a second. We have x plus 2, x minus 1, and then this is the same as x cubed minus 3x squared plus 4x minus 2. And now we only have one more 0. So we can, oh, I run out of space, so let me move over. So I'll move all the way to the top. So let's remember this. X plus 2 squared, x minus 1. Actually, you know what I'm going to do? We'll just copy and paste this thing. Alright. Alright, we don't need to go that far. We're not going to go all the way to the top. We'll just move it over here. Oh no, I lost it. Oh, there we go. Alright. So let's do some more synthetic division now that we moved to this. And we needed to test 2. That was the only one that was left. So our pool of numbers for the function was plus and minus 1 and plus and minus 2. We found out that 1 was a solution. Now all that we have left is 2. So we have 2. And we have 1 minus 3. I need a little bit more room. 4 and minus 2. 1 times 2, that is 2. This is minus 1. Minus 2 gives us 2. 2 times 2 is 4, and this gives us 2. So this is not a factor either. And here a lot of people would maybe start questioning whether they did the problem right or not, because we've run out of zeros. So if we go back to our original pool of zeros, which is right here, we had plus and minus 1, plus and minus 2, and plus and minus 4. And there was one minus. And we found out that x is equal to minus 2, so minus 2 was a 0. So we don't have any more minuses. We tested 1. 1 was a 0. And then we tested, what else did we test? Yeah, then we tested 2. And then 2 was not a 0. And then we found out that 4 was not a 0 due to this new PU over Q. And we can test 4 in synthetic division, and we're going to find out that that's not a 0 either. So we don't have any more zeros to test, but we're still in an x cubed function. And we know that this is an impossible solution, that everything has to have a solution. We can't have 3 imaginary solutions, we know that. So we know we're missing one, because imaginary solutions come in pairs. So if you ever get in a situation like this where you are in an x cubed and you're trying to reduce it down and you can't figure out what it is, what that means is that you have a multiplicity. That means that one of the x's is repeated. And the only one that it could possibly be is 1. So that's our only positive 0 we found. So let's put in 1 again for this equation. We have 1 minus 1 and, oh no, that was wrong line. 1 minus 3, 4, and minus 2. So let's put in 1. 1, 1, 1, minus 2, 2, 2 times 1, 2, 0. So minus 1 works again. So what this means is that we have x plus 2, x minus 1, x minus 1, and then we have this left over, x squared minus 2x plus 2, which we already know is imaginary because we've run out of real zeros. But this is what I wanted to get at with this problem, is when you get into a situation where you have an x cubed or a higher order function, yet you've run out of zeros to test. What that means is that the only possibility, because we know that we had an x to the fifth function, we know it's going to have 5 zeros. They don't all have to be real zeros, but we know that imaginary zeros, let's move down. We know that imaginary zeros come in pairs. Because of the conjugate theorem, if a plus bi is a 0, then a minus bi is also a 0. So we can't have an odd amount of imaginary solutions. So we knew up here when we had this function, this x cubed minus 3x squared plus 4x minus 2, and we tried in our last possible real solution or real zero and it didn't work, then one of them must have been repeated. And thankfully for us, there was only one 0. So we only had to test one. We knew it had to be another 1 because we had no other zeros that worked. So if you get into a situation like that where you've tested all of your zeros and yet you still have something that's not in quadratic form, or you don't have, basically if you've reduced it as much as you can with your pool of numbers and you still have an odd function like x to the third or x to the fifth, because you could not be able to not reduce it, you could get an x to the fourth and have 4 imaginary solutions, and that would be a little bit of trouble for you. But here we know that we can't have an odd amount of imaginary solutions, so therefore there has to be another real 0 somewhere. And the only other option, once we've tested all the zeros, is that one of them is repeated, and that's what we found out. So now that we've done that, we're left with x squared minus 2x plus 2, and we can just put this into quadratic formula and get the answer. So we have minus b, which is 2, so minus 2, plus or minus the square root of b squared, so 4, or I'm getting ahead of myself, it's 2 squared, minus 2 squared, minus 4 times a, which is 1, times c, which is positive 2, over 2a, which is a is equal to 1. So let's scroll down. This is going to be 4 plus or minus 4 squared, or 2 squared, which is 4. Man, I keep getting ahead of myself with that. 4 minus 4 times 2, which is 8, all over 2. So this is 4 plus or minus the square root of minus 4 over 2. The square root of minus 4 is 2i. So it's 4 plus or minus 2i over 2. So this is equal to 2 plus or minus I. So our zeros are minus 2, 1, 1, 2 plus I, 2 minus I. Or we can say that our zeros are minus 2, 1, 2 plus I, 2 minus I, with 1 with a multiplicity of 1. So what that means is that 1 is repeated. Or we can just write it out in linear factors. So we can write x plus 2, x minus 1, x minus 1, or we can just write or we can write it like this. That would be save a little bit of space. We'll just do that. And I keep wanting to write an I there. I have no idea why. It just looks like it belongs there. Man. So any of these would be a correct way of saying what the zeros are. Or we can just write this as x minus 1 times x minus 1, or x minus 1 squared. Either way, these are all valid ways of stating what the zeros of this polynomial are.